Hello, my name is JBryce and today I'll be covering the second part of the knowledge integration. I'm in classes 311, 331, and 341. For the second part of the knowledge integration system, we look at an audio amplifier system. That is consisted of a V in that goes into some audio amplifier, there's some V out, and that goes into some speaker. I'll be doing a signals and systems analysis, a microelectronics and circuit analysis, as well as an electromagnetic analysis of that audio amplifier system we saw one slide ago. Now to break down that first picture just a little bit more, we have a schematic of the audio amplifier, which is consisted of two MOSFETs and a voltage source, two voltage sources, and a resistor. So for this, you have some V in, which is in this case a sinusoid wave that is then biased with another voltage that is then connected to the first MOSFET, M0, runs through that, then it goes into another MOSFET. That voltage input and V in is connected to the gate of the first MOSFET, where the source is then connected to a gate of another MOSFET, M1. And then above that, there's that VDD, which is equal to 1.8 volts that goes through a resistor down once again to the gate of the M1 MOSFET, and that one as well as goes to the source of the M1 MOSFET. The drain of that is our V out that is then connected to a speaker, and we get an end result of noise or sound. Excuse me. So one important thing to note about the system is that it's a non-linear system due to the MOSFETs, and that's something that we'll cover for the signals and systems analysis, but we're going to actually start with the 331 analysis, in which you have that voltage input that goes into the first MOSFET and the bias voltage. If the bias voltage is high, it causes the gain of the whole system to be lower. Therefore, we want that to be a smaller gain, or a smaller voltage bias. That way we have a larger gain across the whole system, and therefore the audio amplifier does its actual job. So, moving on to the second MOSFET, there's a voltage or a source follower, and where the source of that MOSFET is actually run through a resistor, comes back around to the gate. Now, one of the many benefits of this is that it really amplifies the gain of the system. So, by not adding any more parts such as an op-amp or etc., we can just by having a source follower increase the entire gain of the system just by connecting two terminals to each other. Transitioning over to a signals and systems perspective, we have these two graphs. On the left is a frequency analysis where the voltage input is 10 millivolts versus 20 millivolts to see what frequencies are coming out of the system. And on the right, we see just the output, the V out curve, where V in is equal to 200 millivolts. On the left, we notice that at 10 millivolts, there's only two voltage spikes. When there's 0 frequency, and there's another voltage spike at a 1K frequency. However, increase the voltage in to 200 millivolts, and now there's 4 voltage spikes. So these are kind of a ghost phenomena of frequencies where there's voltage spikes at different frequencies. That is due to a Fourier series where the inputs with the input of a cosine wave and a phase shift causes those voltage spikes at those different frequencies. Moving over to the right, we see V out. And with V in is equal to 200 millivolts, we have sort of this half sinusoid wave where it's a half rectified of the input, where on every negative cycle of the input sinusoid is equal to 0. But on the positive input, there's a gain of almost 3 times, as you can see that the peak of the positive cycles is about 550 millivolts, whereas the input is only 200. So that sort of outlays what the gain is for this system right now. And you can definitely tell that it is a non-linear system because it is an input of a sinusoid wave of just let's say, a sinusoid of that goes up to 1, back down to -1. In this case, it comes in at 0.02 or 0.2, drops down to 0 on the negative half cycles, spikes to 0.6 and repeats that, which is not linear whatsoever, which is to be expected because of how the MOSFETs are configured. Lastly, moving on to a electromagnetics perspective, we have the speaker, which takes that V out alternating current basically into those two terminals, positive and negative, which generates a coil generates a current through that coil, which then induces a magnetic field generated by that magnet, causing the coil to move up or down, which then moves the speaker cone, which then generates the noise. So, in essence, with a higher spike in current, we get a louder sound. Altogether, this, as noted before, this was an audio amplifier, which just increases an input signal so that way it can have a higher output, more readable audio sound. It's commonly found in speaker systems, and it has a couple of different applications, but that's it.